Okay, so hello everyone. Uh, I'm going to talk about some very beginner topics. So, first question: who of you have heard of machine learning? Okay, so you might be a bit more advanced than I expected. Uh, Something about me. Uh, I'm working as a consultant for machine learning projects. I also work in academia, glaucoma, in Polish jaskra. We are analyzing some digital signals that get collected from eyes, and we try to have a better way of diagnosing glaucoma. I'm also doing some other things. If you happen to visit Wrocław, let's meet in the data science Wrocław meetings. We are organizing them, well, fairly irregularly, so watch the page. I'm going to talk about my journey through machine learning stuff, starting from being a computer science student who had never thought that he will learn any more mathematics than just a standard computer science course. And I had the luck of joining a bioinformatics company, a small startup in Wrocław, and my first assignment looked like this. I got a table of numbers, and I was supposed to build a cancer biomarker detectors, which, well, firstly, I had no medical or bioengineering experience. I didn't know what biomarkers are, and moreover, I didn't know how to build anything like a detector. And it turns out that it was a fairly nice assignment for the first task, because, well, if you look at this table of numbers, they don't mean anything unless you start aggregating the data, and data analysis is partially a mathematician's job. They are trained to do statistics, but also a computer scientist's job. They analyze data, they collect, aggregate, manipulate data to make something more interesting. And let's skip to something simpler to give you an example of what it takes to build a detector like that. Well, this is a small part of a certain dataset, free open dataset available on the internet about the Titanic disaster. We have a list of rows. Each row represents a single person who either survived the catastrophe or died in that catastrophe. And we had some basic information about each of those people, whether that person survived, sex, age, whether they had siblings or spouses on the ship, whether they had parents or children on the ship, where did they embarked, where their journey started, and we may think of trying to find out some simple model that would predict initially, before the disaster happened, who would survive. And one of the simple types of models, of predictive models, that can be built are decision trees, which they look like a game of 20 questions. We try to guess from the point of view of someone who try to predict who would survive or who would not, by asking some simple questions based on the columns we had in the original data set. And I hope this is a simple thing to follow. If a person was a female passenger, she was likely to survive. The probability was 73, and 36% of passengers were female. And so on. If this was a male, then we ask another question, and then another question potentially, and so on and so on. And well, if you recall the original table, the white one, we would want to build something like that, but for the white table, this one with thousands of columns. However, we need to build a tree, so we need to make several decisions on how this tree should look like. One of the first decision is the shape. We may build the tree in different shapes, like longer, wider, more questions, less questions, and so on, so on, so on. And from the computer scientist's point of view, there's a lot of different trees, exponentially many compared to the number of nodes, right? You can attach those nodes to each other and make the tree large enough to do mostly anything. And the machine learning approach for this is just try something, a simple approach. Let's try recursively. Start from the first question, and when you decide what this question should be, then you never come back to revisit this decision. This question will stay forever in this tree. So let's start from this basic question, the first one. Then when we split the data set into smaller parts, like female and male, we consider question here, and when we decide what should be here, then we go recursively down. So a simple approach, and it turns out it will not allow you to build a perfect tree. Like you have a data set, and it may be possible to make a better tree than with this strategy of local choices. But it turns out that this is a good enough approach to building a decision tree. And this is one of the first things I learned about machine learning. Good enough is very often better than theoretically sound. You may have heard about neural networks, how they started to beat everything under the sun in terms of image classification and so on. In 2012, there was this amazing model built by a Canadian, if I recall correctly, Canadian PhD student, who thought, hey, this nice theoretically sound function of tangent that has a nice derivative and so on is too long to compute. So let's replace it with a simple two linear functions. And it turns out that despite that it never had any theory, it worked much better than this nice function of tangent, because it was much faster. Many algorithms work by performing some approximations and hoping that successive approximations are better and better. And if you can have more steps because they are faster, you can go further in the terms of models and become closer to the optimal model by just making more steps, even if each single step makes more mistakes. Another question when building this decision tree is what questions to pick in each of the nodes. So we had an example of something. Let's try something quickly and make mistakes, but if you don't make too many mistakes, it will go well. Here the usual case is try every single question and find out which is the best one. So you have, let's say, thousands of columns. So you try every one of those thousands of columns. In each column, you may have thousands of different thresholds, like age, 9, 10, 11, 12, and so on. Decide whether to go left or right. Let's try everyone. So we have quite a lot of decisions. And again, it turns out that this is good enough. Why? Because it's fast enough. If you have a smart implementation, then you can sort the table by that column and then compare whether splitting by this or that row works better or worse. What does best mean? This depends on the implementation, but in general, it's something like whether after the split we have more cases positive in one side of the split than in the other, and vice versa. And who knows this quote? When in doubt, use brute force. This was actually said by Ken Thompson, one of the Unix fathers in the 70s. He was not a machine learning specialist. I'm not sure there was a field called machine learning at the time. It was artificial intelligence more. But this simple statement works quite well as long as you don't have too big data. And in case of Titanic, where there are just 2,000 of passengers, in case of biomedical data, it gets even more funny because collecting each single sample, it's a separate patient. It costs a lot. If I recall correctly, it cost about $1,000 to collect one row of data, and it takes a lot of time, and you have to collect all those samples manually. So you don't always have the big data here. Okay, let's say we have built some procedure to build a decision model like a tree. How do you test it? How do you make sure it works correctly? Here's one idea. We prepare simple synthetic data, like in general unit testing. You write some simple procedure, like you compute position. Let's say we are writing a game, and you compute the position of a player, and so on, and you can write a test that if the player was here and he pressed left, then maybe he is here now. And this sometimes applies to machine learning too. The problem is when you want to test a procedure like that, you need to make sure that a model you built is capable of expressing that relationship. And it turns out that decision trees could not, usual implementations of decision trees cannot implement something simple like this. Because what kind of split will you choose as the first one? A or B? They are the same, actually. Whether your threshold will be 0.5 or 0.8, it doesn't matter. They will both segregate the inputs into 1, 0, and 1, and 0 and 1. So they are useless from the point of view of a decision tree. Another example is neural networks. Here are two papers, this one from 69 and from 86. The first one states neural networks as known in 69 are not capable of expressing this table, not capable of learning this simple thing. It took about 15 years to learn that this simple table can be learned only if you have very specific algorithm, like backpropagation, that you have very specific architecture. So when it comes to testing a machine learning model, this approach is not really used. Another approach, random data. In unit testing, we sometimes have an urge to just make some random data and try following it to whether it works. If we can't prepare synthetic data, then it's even more a bigger problem to prepare the random data that we will know will work. So even bigger problem. We can have real data sets and read in the papers that on this data set this algorithm should work. Turns out it takes a lot of time, and I will talk later about why it takes a lot of time. However, if you are actually writing a library to prepare models, every user will compare your library to others by checking whether they can reproduce the problems from the papers, the known problems. For example, if you happen to write a neural network library, everyone will ask, will it work as well as TensorFlow on this dataset? Another approach, compare to existing implementations. So, assuming we have some existing implementations, like in terms of decision trees, there are tens of libraries that build decision trees now. We can just compare whether they work the same way. And when I was doing that assignment, it turned out that, well, I wrote some prototype in Python. Python was simple, so I could test it manually, check whether it works fine, coded those tests. Then I wrote the production code in C++. Our application was supposed to be in C++, then it changed, but things happen. Then compare that my prototype Python implementation to that C++ implementation, wrote some unit tests that compared those two. It was quite a lot of work, but it had to be done to make sure that we don't have any regressions. This bioinformatics company was analyzing data from very specific devices. Those devices tested different samples of biological tissues and were supposed to find out how much of each substance there is in the sample. And the columns here are different molecules, like different proteins and so on. And we were supposed to firstly find out what proteins are in the sample, then do some machine learning on that data set. And at the time, I didn't really know. I was just assuming that the data is correct. But now, whenever I tackle a new problem, I ask where this data actually come from. So I'm trying to investigate what is the path from the, let's say, biological or social or economical issues that result in these numbers. And it sometimes goes to understand a diagram like this. We have this sample, and this specific method was using laser to ionize them, take some electrons so that they are charged, then they are accelerated, and they hit the detector. And it turns out that the heavier a molecule is, the slower it will be in the acceleration chamber, and therefore the detector will detect it later. So we can separate the slower, heavier molecules from the lighter, faster ones. But now, what happens if the procedure accidentally takes not one electron but two? They are charged more, so they are faster in the chamber. What happens if this laser, it turns out it can sometimes destroy the molecule or split it into two parts. If this molecule was too large, like a long chain of protein, it may happen that this protein splits into two smaller ones. And turns out that we are starting to detect smaller molecules instead of bigger ones. So we had to peek into the data, into the initial data. It sometimes looked like that. This is the mass and number of detections and number of collisions with the detector we detected. So in this data set, we see that there is probably a lot of molecules around the mass 2000, whatever the 2000 means. A smaller amount of molecules slightly about 2200 and so on. And we need to somehow extract that data into the table. This is a screenshot of some procedure that tries to extract those data. The initial data may look like this, and you see that there's over-detection of small molecules. As I said, it may happen because of accidental splitting of those molecules. It may happen for different reasons. And we have several steps that try to clean up this data set so that we may end with something like this, where each peak, each line corresponds to a molecule of a specific mass. And we have 1, 2, 3, 4, 5, well, 5 steps here, and we still need to build a table from that. So our software, this was about more than 10 years ago, so it was a slightly simpler procedure, had steps like this: running the biological procedure to extract those detections, loading data, then denoising, then peak detection, then binning, and so on and so on. And each step of those was a vital component of the procedure. Without that, you would not get any good results. And each of those steps could be tuned specifically for a sample, for a machine. Different machines resulted in different problems, and you had to do that well, quite a lot. And this was vital because, well, if you start making changes to this procedure, you will end with different numbers, and different numbers will mean that that the machine learning procedure will result in something different. Less denoising means that the spectra will not hide every single bump in the original spectra, and we'll get more peaks, and more peaks mean we'll get more detections of molecules. That doesn't mean that those molecules actually were in the sample. So, a bit like in usual computer science, when you get garbage data to the point where you are starting a machine learning analysis, you will get garbage output, garbage in, garbage out. And in this case, we can't really make sure that the steps were correct. Every sample was different, and it was the user who had to check whether the steps were correct. We had no idea what kind of samples users were going to analyze. So in that case, about 90% of the code was not machine learning, was not pre-processing, and so on, was just simple mundane things like user interface reporting and so on. And 10% of that was computation, and of that computation, only a small part was machine learning actual. And this machine learning part was very simple compared to the rest of the steps, because it turns out that pre-processing was the more difficult part. And now, when I'm working in the field for more than 10 years now, I see that this is basically happening in every single machine learning project. Whenever you have, whether you have biomedical data or financial data or sociological data or economic data, making sure that data is correct is 90% of the work to perform. And it often turns out that you don't really need some complex neural networks, you don't really need time-consuming algorithms to get good results often. In this case, in the case of biomedical data, a decision tree is often quite good, and if you make several decision trees in different ways and aggregate their predictions, this is close to state of the art. So why bother making something more complex? Let's spend that time on something of better business value. And yeah, making sure that things work is the most difficult part in machine learning, not the algorithms themselves. You can write a decision tree in one evening. You can write a neural network code if you know the formulas in one evening or two. The difficult part is to make sure that if you write the algorithm, it actually works on your dataset or different datasets. And there are two parts to making this kind of code. First one is the usual thing. Is the decision tree actually a decision tree? Are we building more than one level of depth usually? Are the splits chosen correctly from the data? Another part is whether the algorithm chose is actually a good fit for your dataset. Like I said, for biomedical datasets, it's usually decision trees work quite well. For image processing, neural networks work quite well, but you need to know this to make sure your model actually predicts something useful. And when I started thinking about this, writing this slide, I started thinking that this is actually similar to some parts of standard computer science approaches in business, like user interface design. Your designers think of some design, and they may think that this will work, but they need to test externally on users to make sure that their ideas implemented correctly by software engineers actually work in practice. And the same is with project requirements. You go to a client, you talk to him, you collect some requirements, you translate it into code, and then it may turn out that those requirements were not actually what the user wanted. So you need to test it externally. In machine learning, this is a slightly more complex thing because when you make a prediction model, it usually turns out that you don't really know why the model works or how the model works. You may think that this is a simple decision tree, but when this decision tree is 10 levels deep, you don't really know why the splits are like that. Like you have 1,000 columns, you make 10 decisions, and why this column was more important than that column, you don't know. And without that knowledge, you can't really easily debug that thing. It's a black box. So what machine learning specialists do is making sure that it is actually needed, because it turns out in many applications you don't really need even simple machine learning approaches. If you actually need it, you need to make sure it works, and if it works, it's good. The problem is it does not always work, usually, for some definitions of usually. And this is a simple story from the 60s. Marvin Minsky is the founder of the AI lab in MIT, one of the people who started working on neural networks in the 60s. Then he jumped into more complex things. And the story is simple. There was some military application. They wanted to detect whether a photo contains a tank or not. So whether they wanted to quickly detect whether, let's say, an enemy is approaching and so on. So they collected data, photos without tanks, photos with tanks, and they quickly got very simple model of very simple neural network to work perfectly 100% of the time. And after a few hours, engineers noticed that this model doesn't make sense. The model actually classified darker images as tanks and lighter images as not tanks, regardless of the content. Why? Because the photos were developed in a different way, in a different lab. So the photos with tanks were just slightly darker, and the model learned that it's enough to figure out whether a photo is darker or lighter to answer the question. And machine learning models are often like that. They try to find the simplest explanation for the column you want to predict. They are like children who don't want to do their homework, so they find the simplest excuse to make sure that the answer is roughly correct. So how do you make sure that those models actually work? What we usually want is to make sure that the model works on new data, not on the data we collected. The data we collected is like a set of examples we showed for training, but the actual value is making sure it works on new data. And we need to measure it. So the simplest approach is to take a data set, let's say 10 million pictures, set aside some set of those pictures, do not show them to the neural network, train the neural network on the smaller subset, let's say 9 million images, and then test whether it works correctly on those pictures set aside. The network didn't see those data, so we may have some information on how it will work on future data. This is usually called train test split, and it's the simplest way to validate whether your machine learning model works. And it needs some clarification. What does unseen data mean? Because whether you want to measure something, you need to specifically pick those examples for the testing set. So the simplest case, let's say we try to make a model for fashion recommendation, and we have some photos of different clothing pieces from Poland, and we know that this model will need to work in Poland. Like, we are a shop in Poland, so we have customers in Poland, so the model needs to work for Polish people. So when we have this data set collected previously, we take at random some examples for the testing set. And we need to be careful to make this at random and not some manual choice, just to make sure the measure is correct. However, let's say we are now expanding to a different country. Let's take some extreme Africa. It's not a country, but and in Africa they have a different taste for fashion. Well, let's say they don't have winter, one thing. So we know that the model will not work as well. But to measure how well it will still work in Africa, in a different country, we need to collect data from that part of the world. So we need to test exactly what the model in exactly the thing we expect it to perform. And another case, can we say that this model will work in some years later? Like, fashion changes. Some things are less changing, some things are more changing, but still we want to test whether a model built in, let's say, 2018 will work in 2020, in 2 years. Again, we need to make a careful choice in how we build this test data set. And the usual approach is to collect some historical data, let's say from the 90s, and figure out whether this will work for the current time. So again, 20 years, but backwards. This is some estimate of how our model work in the future. And again, when I wrote that slide, I started thinking about it, and we do have some examples of similar testing approaches in other fields of computer science. Let's say databases. Imagine you are building a database for customers, and you want to let users search customers by surname, and it will work quite fine in Poland. But when you migrate it, for example, to China or to Vietnam, it turns out that the indices you built in the database will fail, will bring the database to its knees, because it will be very, very small. Why? Because in those countries, there are a set of names that are so popular that you have literally hundreds of millions of people having the same surname. So firstly, searching by surname doesn't really make sense. And secondly, the indices you will build will be very, very large and very, very slow. Same thing with optimization algorithms. I heard an anecdote where a company tried to apply build some GPS software for Europe, like mapping, like preparing routes, and they bought some algorithm from the States. And it turns out that the heuristics used in those algorithms from the States were very inefficient for European countries, because the type of cities, the way the roads were grown in European cities are different than the cities of America. So let's test exactly the application where we want the algorithm to work. And this is indeed quite a lot of work. It may take 90% or even more time spent on the data analysis, if you don't count the preprocessing, which is a separate thing. So preprocessing and validation are the two parts that take a lot of time. And these are the approaches that make this process somehow manageable. You need good tooling. It's usually necessary to have some kind of an interactive environment to make to experiment quickly. You want to have some language that you can express ideas quickly. In general, you need good tooling, and this tooling is very specific to machine learning at times. For example, tools for managing experiments, they work like you write some piece of code that prepare an experiment of loading data, building a model, validating it, and you want to experiment whether this algorithm or that will work better, whether this or that set of parameters will work better, and so on and so on. And because those experiments usually take quite a lot of time, for example, training a neural network for image recognition may take a day or two. You don't want to run them again and again like unit tests. You want to run them once, then store the result. And when you have hundreds of experiments like that, you need a tool to manage it, to make sure that you are not lost in all the results. So that's all from me. Are there any questions? Okay, thank you.